Ionic solids are made of cations and anions being packed into a 3D crystal lattice held together with ionic bonds. Now, depending on the size and the charge of the ions you use, they get packed differently into a repeatable cubic crystal. Now, I've included some examples down below. If you want to simplify this, you can by drawing a cation that's surrounded on the left side, the right side, above, below, and coming out of the screen and going into the screen by negative anions. And then all you would do is you would alternate so that each ion is surrounded in all 6 sides by the oppositely charged ion. And because I have full charge attraction, it means I have ionic bonds locking these compounds, or locking these particles into position in our solid. So attractive force, ionic bond. Now, because ionic bonds are one of the strongest attractions that are known in chemistry, we have high melting points. And also because it's a strong association, they are hard. But ionic compounds do have a weakness. If, for example, I take a hammer and bash this column here and displace this row of ions down slightly, what will happen is they will be repelled by the opposite charged ion. So if I move this positive down one position, I'll have positive matching up and a negative matching up, which will repel each other, which will cause this crystal to crack. So even though ionic compounds are described as being hard, they are also brittle. They smash easily when they're hit with a hammer. In terms of conductivity, do I have charges? Yes, full charges. Can they move? Not when those particles are locked in a crystal lattice. So they are non-conductive as solids. Now, does an ionic compound dissolve in water? Yes, it does. It does use ion dipole attractions. And you might be thinking to yourself, well, wait a minute. If metallic solids didn't dissolve in water, why do ionic compounds do? If I take this slightly negative O, I can make an attraction between this and that positive cation, an ion dipole attraction. Now this cation, though, is held in 3D by 6 ionic bonds, right? Now, you would think that that would prevent ionic compounds from dissolving. But if the charge difference between the ionic compound is low, only one difference, a 1 plus a 1 minus, then the ion dipole can actually separate those ions apart. Now, what also helps is if I get that cation by itself, I can actually make more than one ion dipole attraction. I can completely surround this ion with water, with the negative O's pointing inward. And because water is bent or boomerang shaped, I can actually slide a lot of waters into the position to create ion dipoles. So I'm breaking 6 ionic bonds, but I'm making over 100 ion dipole attractions. The energy released making those ion dipole attractions is greater than the energy required to break the ionic bonds in the crystal most of the time. So that's why some ionic compounds dissolve. I can do the exact same thing with my negative anion. It can be surrounded by water, making ion dipole attraction. The water just has the opposite orientation, with the slightly positive H's going in. Now, if this attraction becomes too great, let's say for example I had a 3 plus or a 2 minus, I might not be able to make enough ion dipole attractions and get enough energy out to overcome the strength of those ionic bonds. So some ionic compounds are not soluble in water. It depends on the charge difference between your ions. Now let's go back to conductivity. Ionic compounds are non-conductive as solids, but let's look at it as liquid if it's dissolved in water. If it's dissolved in water, my ions are now free to move around in the container. But also too, if I melt this ionic compound, my charges will be able to move as well. So ionic compounds, one way to identify them is they're not conductive as solid, but they will conduct when dissolved or when they're in a liquid form. The last type of solid we'll cover is known as a network solid. You make it by taking atoms or molecular compounds and linking them together using covalent bonds, and they create 3D or 2D patterns. The attractive force that you use is a covalent bond. Now, in order to melt a network solid, you might have to break 100 or thousands of covalent bonds. That's going to take a lot of energy. Because of that, the melting point of network solids is very high. Now, we're talking about the 2000 degrees Celsius range. In terms of hardness, the network solids are supported by their structure. So if you push on one atom or try and crack, the pressure is spread out over the whole structure because of the way it's designed. So they are very hard. In terms of conductivity, I don't have any charges, so they're non-conductive. Solubility in water. I have to take an atom or a molecule that's nonpolar and attach it to a polar water. I'd have to use a dipole-induced dipole. So, because that's a weak force, I have low solubility. Now I've given you some examples of network solids. Now the first are allotropes, or different forms of solid carbon. Here I have carbon atoms covalently bonded in hexagonal rings, and they get extended out in flat sheets. This is known as graphite. Graphite's used mainly as a lubricant, or you put it in locks to make sure that your doors open and close really easily. Because graphite is slippery, people think that, oh, it's really soft. It's not. The sheets are very, very hard, because if I try and push on that atom there, the pressure or the force gets spread over the whole entire lattice. Now, it's slippery because in between sheets, they're only held together by weak London dispersion forces. So the sheets can slide past each other, giving it its lubricant-like properties. Now, this structure over here is atoms that are bonded in hexagons, but they're bonded in 3 dimensions. So the hexagons are coming off each other in 3D. This gives it strength and stability in all 3 dimensions. This structure here is known as diamond. The next one, we have hexagonal rings that are formed into a sphere. It kind of looks like a soccer ball with a carbon atom at each point in the design. You need 60 carbons in order to complete this molecule, so it's known as C60, and its common name is known as a buckyball. It's named after an architect, Buckminster Fuller, who created buildings out of repeated geometric designs. And this last form of carbon here is known as a fullerene tube. More commonly known as carbon fiber. Here we have that hexagonal shape of carbon, and it's arranged into a hollow tube-like structure. Because of the hexagons, it's very, very strong. And because of all the open space in the hollow tube, it's very light, which gives you a very strong and light construction material, which is why they make sailboat sails out of it, hockey sticks, ski poles, things like that. The last example here we have is a molecular network solid, and that's because the repeatable unit is an SiO4. And so you take that and you just covalently bond that subunit together. It's known as silicon dioxide, even though there's 4 oxygens in each subunit, and its common name is quartz.